Morning. My name is Caroline Cardinal, and I will be hosting the talk today. So let me just share the application I will need for today's talk. And we will just be able to go. Here we go. So for today's webinar, in terms of question, as a question about curve fitting, on the topic are quite complex. It will be better if you actually send them to me via email. So at the end of the presentation, you will have my email address. And if you have any questions on today's talk, or if you want to have the presentation or the protocol we will review, please send me an email. And I will answer the question and give you back the information. So today's talk will be on curve fitting features and PLA as a practical guide in SoftMax Pro 6. So as I'm not a statistician or mathematician, we will not cover the theory, the formulas, or high-level stats. But today we'll cover curve fitting, what is weighting, what is PLA, and what are confidence intervals. For the first three topics, so curve fitting, what is weighting, and what is PLA, we'll also review some protocols that have been written in SoftMax Pro to help you choose the best curve fit, the best weighting factor, and to determine if the curves are parallel. So first of all, what is weighting? When choosing the best curve fit equation is really important as it should represent the most accurate relationship between two known variables x and y. The goal is to find the parameter value of the curve fit equation that most closely match your data. Therefore, it will give you better experimental results, such as the rate changes, higher and lower asymptotes, and the EC50. SoftMax Pro will help you do just that with its now 17 curve fits plus a point-to-point model. So in terms of flavoring, so you can have two types of curve fits. You have the linear regression and the nonlinear regression. For the linear regression, they are quite simple. You will need only 3 data points in order to use that regression model, and you can choose from linear, semi-log, or log-log. Here you have an example of a linear regression, which is described by the equation y equals a plus bx. Unfortunately, most biological data are not following a linear regression, and you will have to choose from nonlinear regressions. In SoftMax Pro, nonlinear regression are described with the Lovenberg and Marquardt algorithm, and it will help you best fit your data. For those type of regression, you need 6 points in order for the curve to be well described. As an example, you will have the quadratic, the log-logic, the cubic spline, the exponential, and the famous 4 and 5p parameter curve fit. The 4p and the 5p parameter curve fit are sigmoidal functions that will produce a maze shape. The 4 parameter curve fit is symmetrical with the lower and the higher asymptotes symmetrical with the EC50 in the middle. However, when your data are not symmetrical, the 5 parameter curve fit model may be better as it will allow some flexibility between each half of the curve by the introduction of an extra parameter G, for the asymmetry. So choosing the best curve fit can be tricky. And there's a protocol in SoftMax Pro that has been developed to help you do just that. So this protocol is using several methods in order to help you determine which curve fit evaluated is best. So it is still quite widely used that the R-square can help you determine which curve fit is best. And if it is greater than 0.99, then it will show you a good fit. However, it will be misleading if the standard deviation changes with the concentration. Therefore, the protocol has been implemented with two other methods, the sum of square method and the Ake method. So first, the sum of square method we calculate the sum of the observed response minus the predicted response square multiplied by 1 divided by the variance at that concentration. The best curve fit will have the smallest sum of square error. However, you will need the F-test to confirm the result given by the sum of square error. And this is because the model with the more detailed equation, so the model with the more equations, the more parameters have a lower sum of square error because you will allow more inflection points to fit the data. And therefore, you need the F test and the F probability to confirm that adding an extra parameter, so losing a degree of freedom, is worth having to decrease the sum of square error. If the probability is lower than 0.05, then it means that the model with the most detailed equation is a better representation of your data. So this has been implemented in the protocol. Another method that has been implemented in the protocol is the Yake information criterion method. And this method uses the likelihood statistics, but it can also use the sum of square error. So here, in SoftMax 4, it has been implemented with the sum of square error. And as for the previous method, the best fitting curve has the smallest Ake or Ake-C, which is calculated as the sample size multiplied by the log of the sum of square error divided by n plus 2k. If the sample size is below 40, then the equation changes slightly, and this is the equation that has been implemented in the protocol. So n is the sample size, k is the number of parameters, and therefore you can see that because you're adding 2k, you're actually penalizing for curve fits that have more parameters. So therefore, you don't need additional statistics to confirm that the curve with more parameters is best for the data. Here, the Ake method will penalize for the addition of parameters, and therefore it will select a model that fits well but has a minimum number of parameters. So there's a lot of more methods available in order to choose the best curve fit, but here we have just selected a few. In addition, all these methods do not measure the goodness of the fit, and if you are evaluating only poor models, then SoftMax Pro will logically select the best of the poor model. So you have to be careful of which model you're actually evaluating. So now there's one way to study the goodness of the fit, and this is by plotting residual. So basically, the residual plot is basically normalizing the data because you will be plotting the error versus the concentration. So there's various methods in order to measure the error, but in this protocol, we are measuring the Y error, and therefore it will be calculated as the observed response minus the predicted response. The residual should represent the random error, and therefore, here you can see that I have now a graph showing you the residual plot. So we are putting the residual, so the observed response minus the predicted response against the concentration. And if the model fits well the data, then the residual should be randomly scattered around the zero line. However, if the residual displays a systematic pattern, then it means that the model fits poorly your data. And you can see here, now in this new graph, I have a systematic pattern showing me that clearly my data should not be plotted as they are here. So now let me show you the protocol in SoftMax Pro. So this is the protocol on the curve fit, and actually the four protocols we're going to see today have exactly the same configuration. So first you have some note section. One will be for the introduction, so I will describe you what's going on with that protocol. Then you will have a result section, which will basically bring you the conclusion of the experiment. So as soon as you have your plate populated with data, so as soon as you click on read, or you have copy and paste some data, this result section will automatically be populated with the conclusion. So here we are evaluating a curve fit, and it will tell us, according to the sum of square error or to the Yake method, which curve fit is best. With the sum of square, we will be using the F statistic and the F probability too. In terms of data analysis, you will have some group sections which will show you some calculations that were necessary in order to get to the conclusion. And here we will calculate the residual for a 4-parameter curve fit, the residual for a 5-parameter curve fit, the sum of the square error for the 4-parameter curve fit and the square error for a 5-parameter curve fit. So the data in that protocol are plotted into a 4-parameter curve fit and a 5-parameter curve fit. So the residual can be calculated from those two fits in order to give you the best curve fit model describing the data. Finally, you have the residual to help you see which model is best if there's a model that's completely breaking down and to study the goodness of your fit. But most importantly, the result section will just give you straight away which model is best for your data. So there's nothing to play with. Let's go back into the presentation. So here, this is exactly the conclusion of the protocol I've just shown you. So the data were fitted into a 4-parameter curve fit and a 5-parameter curve fit. And the R-square for both curve fits was 1. So it was really difficult to see which one was best. But looking at additional statistics, so as the sum of square error, we could see that the sum of square error was 0.27, so it was lower for a 5-parameter curve fit than for a 4-parameter curve fit. The F statistic for a 4-parameter curve fit was very low, so it meant that the F statistic was confirming that it was a 5-parameter curve fit. And looking at the AXE method, we could clearly see again that the 5-parameter curve fit gave a lower value and therefore was best describing the data. So the conclusion from all the statistics and from the residual plot show that the 4 is a better than the 5 is a better curve fit model than a 4. So here, if you look at the residual, you can see that so my 4-parameter curve fit being the red dots and the 5-parameter curve fit being the blue dots. You can see that both models actually well describe the data because they are randomly distributed around the 0 line. However, you can see that the blue dots are actually much closer to the 0 line than the red dot, and that therefore the relative error is lower for the 5-parameter curve fit than for the 4-parameter curve fit. So in SoftMax Pro 6, and something quite new that will help you measure the suitability of the curve fit without doing any calculation, and that is the parameter dependency. So the parameter independence will be calculated, and it is based on the principle that the best value of one parameter depends on the best value of other parameters. So the values are generally between 0 and 1, with 1 being ideal, and in SoftMax Pro, it has been translated into bars. But let me show you how to implement this. So as default, it is not selected, and you will have this will be available for all curve fit models. In order to select it, you have to select the sigmoidal curve icon onto the graph menu. So this is the graph options. Once you are selecting this, the following window will appear, and you have to select the statistic option. In the statistic window, you have to select Calculate Parameter Dependencies. Once this is selected, you will see that below the graph, you will have an extra column that is called Parameter Independence. And you will have a box with bars inside showing you if the parameter is well described by your curve or not. So if you have 10 bars, then it is a good curve fit. If you have 0 bars, then the fit is actually poor. So let me show you an example. So here I have, again, this is a 4-parameter curve fit. And you can see that my curve is quite well described by the curve well described my data, and I have the higher, the lower asymptote. All my parameters can be calculated from my curve with no problem. And here you can see this with independence. Independence for each parameter is between 7 and 9. So all the curve is a good curve fit. However, when I have a 4-parameter curve fit where the higher asymptote is missing, all the parameters describing the curve that are dependent on that higher asymptote described by parameter D, then the independence is dramatically affected. And you can see that parameter D and C have only 1 bar, so showing a very poor definition of that parameter, parameter B, the slope, is also affected because the higher asymptote is not defined. Only parameter A show a good independence because we have a nice curve in the lower part. So basically, when you have either some part of the curve that is missing, you will have a poor independence of the parameter that were described by those values. So here we have the fit is not appropriate for the data. So now we have covered the curve fitting. We're going to move on to weighting and what is it and why to use it. So choosing the proper weighting factor is crucial for obtaining the best curve fit and therefore finding the curve fit parameter values that make the curve fit model chosen as close as possible to the measured data points. Weighting will affect the influence of the data point at each concentration and give importance or more weight to certain data points or particular part of the curve fit model. Weighting has been developed to account for the difference in absolute error at the bottom and at the top of the curve, because generally the absolute error is larger at the top than at the bottom. This means that the standard deviation varies with the sample concentration. The problems arise from the fact that the large standard deviation at the point at the top of the curve dominate the curve fit and therefore the calculation of the curve parameter. Therefore, choosing the proper weight factor will allow you to adjust the curve to be tighter around the standard response with a smaller variance, typically those with a smaller response, and looser around the standard response with a larger variance, typically those with a larger response. So how can we have a look at the data and determine which one needs to be weighed and which one doesn't need to be weighed? So, for the record, some statistician will even tell you that even not weighting the data is still, you are still applying a factor of 1, and therefore you cannot really say that you are not weighting them because there's still a weighting factor involved. But here, for the simplicity of the presentation, we're going to say that if we're not applying any additional weight, then it will be no weight. And if we are applying a factor different to 1, then it will be a weighting factor. So, for example, you can see that on your left, you can see that I have a case where my standard deviation is constant, and therefore my data do not generate any scatter. And this is a case of homoscedastic data, and for those type of data, weighting is not going to be beneficial at all. However, on the graph on my right, you can see that I have the standard deviation is increasing with my concentration, and therefore I am generating a scatter, a variation within my data set, but it is not random. So here it is linked to the concentration, but it can be linked to time or to the number of data points. So the variation, the scatter generated must not be random. It must be linked to something. And in that case, I have heteroscedastic data, and weighting is probably going to be beneficial. So how do you use it in SoftMax Pro? So weighting is available for all curves, and but it is indeed very useful for 4 and 5 parameter curve fit that work by minimizing the vertical error between data points of the curve. The resulting curve fit may therefore miss all the data points at the lower concentration, leading to inaccuracy of interpolated data. So weighting will overcome this issue and will give you a better curve fit that is closer to the true value and will calculate more accurate estimates. So for those type of curve fit, it is quite important to evaluate if weighting is necessary. So now we're going to review some weighting factors. And same again, those weighting factors have been implemented in a protocol for testing which weighting factors is best. So the first is the reverse of the response. So 1 divided by the response square, or 1 divided by the response. And this is used when the scatter is not the same at all points, but you assume you know how wide is scattered. So it is linked to concentration, time, or number of points. So you have two types. So the 1 divided by the response square, and this is called the relative weighting, and this is what it is most often used in SoftMax 4. It will be 1 divided by the value square, And this is when the error of the data is not exactly, but you know some information, such as the standard deviation or the CV. And you have multiple data sets that you are analyzing, and the relative error for each data set is known. The following weighting factor is 1 divided by the response, and this is called the Poisson weighting. And in SoftMax Pro, it will be 1 divided by the value. And you use it when the response follows Poisson distribution, and this is generally an error during counting. So, for example, radioactive counting. So the reverse of the concentration, so 1 divided by the response square, by the concentration square, or 1 divided by the concentration. And it will weight the points on the left part of the graph more than on the right, and therefore it is very rarely used. So now the reverse of the observed variability, so 1 divided by the standard deviation square, and this is used when the scatter is not the same at all points. And in SoftMax Pro, it will be 1 divided by the standard deviation square, or 1 divided by the variance. So some statisticians do not prefer this method over do, and this is because they like it, because it's using 1 divided by the standard deviation square allow more weight to be assigned to data points with low scatter, so a low deviation. However, a group of replicates with large standard deviation or small standard deviation does not tell you how close the replicates are from the true value or from the curve. So even if it's with a small standard deviation, you're not sure that this is actually a true value. So when to use it? You use it when you know how Y is scattered, and when you have numerous replicates to reflect consistent variability. Other weighting factors are available, so the reverse of the sum of square, the Turkey B weight, but we're not going to be discussing them today on that presentation. So weighting in SoftMax Pro. So the default curve in SoftMax Pro is unweighted. And you have to, once again, select the sigmoidal graph on the graph menu. And you will have the following window. You have to select the weighting option. And then you will have this window that will appear on your screen. From that window, you have to select the drop-down menu, and it will show you all the curves that you have on your graph. And you will have to select the curve that you want to weight. Each curve on the graph can be plotted independently. Once you have selected the graph, the curve to be weighted, you have to select Apply Weighting and select this little FX. Once this little FX is being selected, you will have a window that will allow you to enter either a parameter that will represent the weight, so a column that has been added into your table representing the weight, and in my case, it was called 1 divided by the standard to weight, or you can enter a mathematical function straight away into that window. So 1 divided by standard deviation square. Both methods will give you the exact same result, and you can see here that on that graph, I have now a curve with no weight, that is in red, and a curve that has been weighted in green. So in those data, weighting the curve is probably not the best, it's not necessary, because I can see that my standard deviation is quite small and quite constant throughout my data, and also because now the green curve is moving away from my point, and therefore I'm going to increase the error with this new curve. So the protocol has been implemented with various weighting factors in order to help you determine the best weighting factor to apply to your data. The first thing is to choose a curve fit model, because that's the first step in your data analysis. This protocol once again uses the R-square, the sum of square error, and the AIC or AIC method to determine which weighting factor is best, and they will give you this. They will be the one that gives you the smallest sum of square or the smallest AIC. That will be the best weighting factor. We are also plotting residual to illustrate where each model is breaking down. And let me show you how it is done in SoftMax Pro. So those are exactly the same data that have been plotted into a 4 and a 5 p-parameter curve fit. So for all the data, I've chosen a 5 p-parameter curve fit. This protocol has, once again, the same backbone. So you can see I will have introduction, the result section. As soon as my data are populated in my plate, the result will be waiting for me straight away, so I have nothing to do anywhere else. So here you can see that for the data I've been using with the 5 parameter curve fit, the no weight is better for my data. You have underneath the conclusion additional information such as the R-square, the sum of square error value, and the age criterion calculation. For each weighting factor, so the data have been populated in my plate. For each weighting factor, some calculation has been done in a table. So you will have the weighting factor applied, the square error, and the residual that will be calculated automatically. You will have a graph showing you the scatter, and then you will have a graph with every time the weight applied. So let's see how we did it. Selected the little sigmoidal curve, weighting, we select the curve that is available on the plot. Here I have only one, and then I apply the weight, and I enter my formula or the column describing my weight. Selecting OK, this will apply the weight on my curve. So the curve have been plotted with either no weight, 1 divided by the response, 1 divided by the response square, and 1 divided by the standard deviation square. In addition, I've got a residual plot to show me how my model are behaving. So we're going to study this inside the presentation. So here, this is the exact same data I've been showing you. And so I've been feeding my data into a 5 p-parameter curve fit, and now I'm going to study the weight. So here you can see that the scatter curve show me that actually my standard deviation is constant throughout my data point, and it's quite small. So it is probably a case of homoscedastic data. So therefore, the conclusion should be probably no weight. But let's see. So here I'm fitting the curve with either no weight, 1 divided by the response, 1 divided by the response square, and 1 divided by the standard deviation square. So you can see between the top two graphs that, it is very difficult to see the difference between the no weight and 1 divided by the response weight. When you increase the weight at the point, so for example, with 1 divided by the response square, you can see that now my curve is moving away from the point at high response. With this 1 divided by the standard deviation square, the more weight will be applied to the point with a lower standard deviation, which is at the top of the curve, so at high concentration, and my curve is moving away from the point at low concentration. So just looking at those two graphs, I can clearly see that those two weighting factors are not going to be good for my curve, and therefore it will be either no weight or 1 divided by the weight, 1 divided by the response. In the protocol, looking at the residual, I can see that 1 divided by the response square, so the blue points, you can see that at high concentration, I was moving away from my curve, and I can see that straight away with the residual, because now I have a pattern, I have a schematic at high concentration, and therefore this model is not good for my data. So the 1 divided by the standard deviation square, you can see here at low concentration, here again I have a schematic, which means that my data, this is not good, the 1 divided by the standard deviation square is not good for my data. With the no weight and 1 divided by the response, the data are well scattered around the 0 line, which means that those models are probably okay. Looking at my conclusion, you can see straight away that SoftMax Pro will tell you that you don't need any weight for those data, and you will have the supporting information with the R-square, the sum of square, and the age information criterion method, showing you that those are the lowest value and therefore the best weight to apply to the curve. So now another example with the case of heteroscedastic data. So in that case, you can see clearly that my standard deviation is now increasing, and it is increasing as my concentration decreases. So once again, I'm putting the whole data into the same protocol, and I will have the 4 graphs with no weight, 1 divided by the response, 1 divided by the response square, and 1 divided by the standard deviation square. And you can see that looking at those 4 graphs, it is not as easy as before, because there's so many curves possible, so many possibilities for the curves to go through, that it will always go through the point. And therefore, I just cannot say which curve is best, just looking at those curves. And I need to have a look at my residual. And same again, the residual is quite hard to interpret, because here, all the curves, all the points are so closely together, and all the points are just randomly distributed around the 0 line. So there's no other way than looking at the statistics. And my statistics here are showing me that I will weight by 1 divided by the response square, and which is quite logical, because I was increasing my standard deviation at low concentration. So it was linked, it was the best weighting factor to use in that case. This is confirmed with the supporting information section, which will show you that the R square, the sum of square, and the H is giving you the lowest value when the weighting factor is 1 divided by the response square. So now we have defined how to help you how to define the best curve fit and how to define the best weighting factor. We will give you some tips. So the tips should be best evaluated when you do a method development of method validation, and you should do it with a significant amount of data in order to account for the variation. So now we have covered weighting. We will move on to parallel line analysis, or PLA. So what is PLA? So PLA is a method to show parallelism between sets of dose response data. And it will be used to evaluate biological data, to compare a known curve versus an unknown dose response curve and look for the differences. This will also help you to determine the relative potency. So PLA will determine if biological response of 2 substances are similar, or if 2 different biological environments give you similar curve for the same drugs. The application are various, but they will come into 3 different families: drug comparison, lot-to-lot variation, and that will even help you to validate your assays, and inhibition studies. So how it is used? So in order to compare curves, they need to be parallel. And therefore, you will be looking to a shift left to right on the x-axis. So you have several types. So the first type is the linear, and you will use the slope difference method, and you will compare 2 different linear curves. Then you have the case of nonlinear regressions, and in that case, you will be able to use, once again, the slope difference method and a constraining curve fitting model. So we will review all this in the next slide. So the issue with PLA is that when you're determining if mathematical functions are parallel is easy. However, to determine if an empirical bioassay data is parallel is not so easy. And this is because experimental data can be variable. You have noise, you have scatter, and this is why sometimes you will have reason to wait or to constrain your curve. In addition, parallel analysis methodology is not set and evolves with time. People find better ways to do things, and this is implemented all the time as we go on. There are also different methods, different models, and the difference lie in determining the metrics for assessing parallelism and also on resolving the question of variance. How the results, and there is enough noise and scatter. So first of all, let's see the simple case. So when we have linear curves. So in that case, we will define parallelism with the identical slope method or the equivalence testing. And here we will have a constant between the sample and the standard curve, and this is going to be the relative potency. So how does it translate mathematically? Well, basically, the slope of the reference curve and the slope of the test curve should be equal. So a protocol has been implemented in SoftMax Pro, and it is based on the slope difference method described by Callahan and Sargent D, that you have the reference below. It is slightly different from the European pharmacopée, which is using the slope ratio. The first step of that protocol is to determine the standard threshold D. So what we call D is actually the acceptable variation, the variation between the slope of the standard that becomes the acceptable variation between the reference curve and the test curve. So this is calculated on 4 curve minimum, and the protocol has all the calculations done for you, and it will calculate the square error, the difference between those errors, and the lower and the upper bound. So it will calculate the larger absolute confidence bound. So D can be, the formula for D will be the maximum of the standard error multiplied by a risk multiplier, which is 2. So in the protocol, this will become the acceptable variation between the test curve and the reference curve. Once you have calculated D, you will have to test for parallelism between the test and the reference curve. So both curves will be plotted, and you will calculate the difference between the slope, the standard error, and the bounds, the lower bound and the upper bound, and if the highest of that bound is within D. So the null hypothesis is that the curves are not parallel, so the difference between the slope is too large to be considered parallel. Rejecting that null hypothesis is to prove parallelism, so it's saying that the difference between the two slopes is small enough for the curve to be considered equivalent. So let's see the protocol in SoftMax Pro. So same again, the protocol has exactly the same anatomy than before, a small introduction, a conclusion that will once again give you, as soon as you have put your data in, will give you the conclusions. So here that my curve can be considered parallel. You'll have some additional information on the relative potency and the slope of the curve. The first step is the determination of D. So you can see that I have my standard. And here, as an example, I have only one duplicate per standard, but in real life, you will have much more duplicates than one. But it is only for the example. The curves are then plotted as a non-linear regression, as you can see here, and you have some calculation done on the slopes. So here, each slope has been tabulated, and then you need to do all possible differences between the slopes. Then you calculate the standard error, difference between the standard error, and the lower and upper bound calculated being the maximum between the standard error multiplied by a risk multiplier of 2, D being the highest of those values, and therefore the acceptable variation between the slope of the test and the reference. In another plate section, we have now the reference curve and the curve that has to be tested to determine if it is parallel. Both curves are once again plotted into a linear regression curve, and data are analyzed by calculating the difference between the slope, calculating the standard error, and the upper bound, the upper confidence bound and the lower confidence bound, saying that those two, in order to be considered equivalent, they should be below D, and the answer for that case is valid. This conclusion is resumed in the conclusion section at the top of your protocol. So this equivalent testing can also be used for nonlinear regression. Some people do this exactly the same for nonlinear regression curve, where they will look at the difference between only the slope and calculate D. So they will calculate the difference between the slope of the standard, and then calculate if a standard curve and reference curve it can be considered equivalent if the difference between the slope is smaller than D. Other people even look at each parameter, and each parameter is tested by calculating the difference of that parameter and calculate a D for each single parameter in order to study the curve as a whole. So this method can be challenging in the way of establishing the threshold D, because if it is too large, then it is easy to demonstrate parallelism. However, if few test curves will be invalid, and the danger is that you will accept invalid curves. However, if it is too small, then it will be very difficult to demonstrate parallelism, and many curves will be invalid. So the danger is rejecting valid results. So establishing D is really important. So now we're going to move on into PLA for nonlinear regression, and this is called the constrained curve fitting. So SoftMax Pro, in SoftMax Pro, it's based on the following reference: the GOT, TAC, and DONE, and you have the reference just below. So this is also available for all curve fit models now in SoftMax Pro 6. And what will it do? Well, in SoftMax Pro, it will simultaneously fit the standard and the sample data to parallel curves, and it will constrain the curve to fit the assumption of parallelism. Then SoftMax Pro will compare the constrained model, so the fixed model, to the free model or the independent model. And you will be looking for the differences in the goodness of the fit, which might be attributed to non-parallelism. So if you have too many differences between the free and the constrained model, then the curves are not going to be considered parallel. However, if you have few differences between the two models, then the curves will be considered parallel. So what will define parallel? So basically, depending on which curve fit model you're choosing, it will be slightly different, but all the parameters will be identical except parameter C. So you will have an identical, for the 4P and the 5P parameter curve fit, you will have identical slope, identical asymptote A and D, and identical G. However, parameter C will be the only variable, as you can see here. So as I was saying, for those nonlinear regression, you will have other possible options, which would be to determine the equivalence for all the parameters when fit independently in the slope difference method. And also you have other methods that will look at the curve as a whole, and that requires different assumptions, so it's not possible here. So in that case, the null hypothesis is that the sample and the test curves are parallel. So skeptics will tell you that it never proves parallelism, but you will have to start somewhere. So testing this hypothesis by comparing the constrained curve fit to the independent fit will be done using the chi-square, and that's only for graphs that have been weighted, and the f-test. You have the formula here just for your information. So in SoftMax Pro, you have protocol available. Once again, they have one-click method. As soon as you have put your data in, everything will be calculated for you. The relative potency will be expressed as a ratio. Both the chi-square and the f-test have been implemented. However, you have to be cautious because they will respond differently to the variability of the data, and therefore they might report different results. In both cases, the null hypothesis in SoftMax Pro is that the probability closer to 1 gives you a greater confidence in the assumption that the sample curve and the standard curves are parallel. So how do you enable PLA in SoftMax Pro? So you select, once again, the graph option, and you have the curve. In the curve fitting option, you will have to select global fit. So if you select global fit, then the curve will be constrained. If you select independent fit, then the curve will be free to go according to the parameter description. Then you will have to select the fit that you want to apply, and you can change this here. So you can see that it is available for all those curve fits. And finally, you will have to select which curve on the graph is going to be your reference plot. Once this is done, you have an option to fix or seed to a certain value or formula, and this will be available for the constraint or the independence model. And basically, you will have to select the little drop-down menu next to the parameter, and you can select none, fixed, or seed. Once you have selected fixed or seed, then the effects will become highlighted. And if you select the effects, the following window will appear, and you will be able to enter a formula or a value. So, for example, 0, or here, I want all the curves on that graph to seed to parameter D. You can see that now into my curve fit window, A is fixed, is seed to 0, and D is fixed to parameter D of the sample. So now, before going to confidence interval, we're going to review in SoftMax Pro the protocol on parallel line analysis for nonlinear curves. So here you can see that I have, in that protocol, once again, I have a note section with a result note section, which will once again give me my result as soon as data has been entered into the plate section. And here you can see that straight away my chi-square and my h-test will give you the information that I need, so that there's 99% confidence that my curves are parallel in both cases. So in your plate section, you will have your data, and you will have both tables to analyze your data and have a column for weighting factors. We'll have one graph with no PLA and one graph with parallel line analysis. You can see that if I select this little curve, I am now acceding to my curve fit settings. I have selected a global fit. I can change my curve fit model. In that case, the reference plot is my standard. I don't want to change any parameters. And if I click OK, then PLA is applied on my curve. So it's very simple to use and to implement inside SoftMax Pro. So now the final topic is a confidence interval. So confidence interval is a way to express the uncertainty of a parameter as a range. And it will be based on the probability that the true value of that parameter lies within that range. So in the example here, basically there's 90% confidence interval that B, for B to be between 1.7 and 2.4, which means that there's 99% chance for the true value of B to lie within that range. So the confidence interval is defined with two things: the interval level and the interval limit. The interval level is expressed as a percentage, while the interval limit is expressed as a lower and an upper value. So the value will show, it will show how uncertain you are about that parameter. And the best choice, of course, is when it is the shortest. If it is too large, you will need to collect more data. So there's two methods for calculating confidence intervals. So you have the asymptotic approximation, and in that case, it is a symmetrical confidence interval. The accuracy gets better and better when the sample gets larger, and it is nearly always possible. The other method implemented in SoftMax Pro is a profile liquid method, and those methods are actually asymmetric, and they are generally wider, and in some cases might not exist, but they are more complex and slower to implement, but they are numerically exact. So which one to choose is generally determined by your statistician, as they know how your data are distributed, because you will need to know how your data are distributed. In SoftMax Pro, as default, the confidence interval is not selected, and you will have, in SoftMax Pro 6, it will be available for all the curve fit models. So once again, you will have to select the sigmoidal curve icon on the graph menu, and you will have to select the statistic option. In the statistic option, you will have to select the confidence interval method, and you will have a drop-down menu helping you to choose between the asymptotic approximation or the profile liquid method. And here you will have 3 different cases depending on if they follow an F distribution, a t-square distribution, or a t distribution. Once the method has been chosen, you will have to choose the confidence interval level. Generally, we use 95 or 99%. Finally, you have to go back into the curve fit window because you will have to select which confidence interval you want to display. Is it for all the parameters, or is it for only some of them? And also, do you want to do it for the relative potency if you have selected PLA only? Once you have selected the parameter and the relative potency, you can see that now below your table you have an additional column that will appear where it is for confidence interval, and it will give you the confidence interval calculated for each parameter of your curve. For the curve where PLA has been applied, you will see that it is calculated on the confidence interval and also, on the relative potency and also on the curve fit parameter. So today what we've covered, well, we've gone through a lot. First, showing you the curve fitting and the protocol helping you to choose the best curve fit model. Finally, we've been able to explain to you what is weighting and how you can test different weighting factors using a protocol inside SoftMax Pro. Finally, we have covered PLA and the method that have been implemented in SoftMax Pro and its protocol. And finally, we have covered the confidence interval and how to implement this in the software. So now I'm just going to close that webinar with this small conclusion. So there's now some data trending available with SoftMax Pro 6, and this is done with a third-party software. But some protocol has been developed in SoftMax Pro 6.1, so trending can be done very easily between the link between the data and the trending software can be done very easily. So what is data trending for the ones that don't know? Well, it is the practice of collecting information from an assay, for example, the mean OD or the curve fitting parameter or the EC50, and to attempting to spot a pattern or a trend through time. So here you can see that for this experiment, we basically we got the mean calibrated OD for a sample, and this value was collected through a long period of time. This will help you to notice a change in the behavior of the assay and correct it before it has reached high limits or it has reached a stage where there's an issue with the assay. So this helps you really see the trend in your assay through time. So there's a webinar available through the link that is on the screen, and we will also do a webinar in Europe next year on trending. But if you are interested, please contact us, and we'll send you all the related information on trending, on the possibility of data trending in SoftMax projects. So if you have any question, as I said, this is quite an heavy topic that we covered today. So if you have any question or need the protocol or a copy of the presentation, please contact me on caroline.cardonel@moldev.com, and I will send you and the information and answer your question as soon as I can. So I hope today's webinar has been useful, and thank you so much for joining us, and have a nice day.